Hi folks, welcome again to Physics with Captain Rod here, and the purpose of this video is to introduce a concept called kinetic energy and what it's about and why it's calculated the way it is. So, imagine, some sort of system object, doesn't really matter what, and there's a series of forces acting on it, but those forces, maybe I've got like an F1 and an F2 and maybe an F3 here. Right? Remember that these forces can be added vectorially, and these three forces together will add to some net force. So I'm just going to replace these with one single force. Whoops, one single force to the right, and call that the net force acting on the system. Now, by Newton's second law, the net force is equal to mass times acceleration. So I'm going to go ahead and write that equation actually down here. Give myself a little room here. The acceleration, though, can be written change in v over change in t. That would give us the average acceleration over a time interval. Now, in one of my previous examples, I talked about the quantity called work. So, remember, work is force times distance. Now, imagine this object moving now a displacement, let's say to here. This is going to be a delta x, a change in position. Then the work done by the net force would equal F times delta x. When I look at this equation here, Newton's second law, if I multiplied both sides by delta x, this is what we would have. The left-hand side, this right here, this is now equal to work. This is the work done by that force on that particle as it moves the distance delta x. And the right-hand side, we can mess around with quite a bit here. So I'm going to have work equals m. Now, let's talk about this. Delta v. Delta anything can be expressed as final minus initial. And, going back to the beginning of this example, I didn't really specify whether this had an initial velocity or not. So let's say it does. Let's say it has an initial velocity. I'm going to call that v sub o. And then this force is applied through a distance delta x. So here's kind of a picture of the object. It has a new velocity, which I'm going to call v final. Then the delta v can be written v final minus v initial, because delta anything is equal to final minus initial. This delta x over delta t here, we can basically group those two things together. Delta x over delta t is the average velocity acting on the particle. Or, I'm sorry, the average velocity of the particle. So the average velocity, if we start at v initial and we end up at v final, the average velocity we can write v final plus v initial over 2. In this equation now, we can massage it up a little bit here. So the work done on the particle is going to equal, so this 1/2 m I'm going to bring out in front, so 1/2 m. And when we multiply this out, this product is v final squared. The outer product is plus v final v initial. The inner product is minus v final v initial. Now those add to 0. And then the last product is minus v sub o squared. So, cleaning this up just a little bit more, we have work equals 1/2 m v final squared minus 1/2 m v initial squared. So these terms, the mathematical term 1/2 mv squared is called kinetic energy, and this is how it's calculated: 1/2 mass times velocity squared. And this mathematical term would represent the final kinetic energy of the system, and then this term represents the initial kinetic energy of the system, and this is the difference between the two. So this equation basically is saying the work done on the system is equal to the change in kinetic energy of the system. So I'm going to take a moment, pause this, clean the board up, talk a little bit more about kinetic energy and this equation here. So just give me a moment. Alright, I'm back. Clean that video up just a little bit here. So, again, just having a little bit of a theoretical conversation here. So, just got done talking about how when you do work on a particle, that work can change the kinetic energy of a particle. And the kinetic energy, the change in kinetic energy, can be written 1/2 m v final squared minus 1/2 m v initial squared. I like to write this equation like this. 1/2 mv initial squared plus work done equals 1/2 mv final squared. And basically what this is saying now is that, you know, if I have some sort of system, that system will have a certain kinetic energy equal to this. Add work to that system by applying a force acting through a distance. I now have a new kinetic energy equal to 1/2 mv final squared. This is just a scalar equation. It follows just basic, I like to call it M&M arithmetic. For example, if I start with 3 M&Ms, I add 5 M&Ms, I now have 8 M&Ms. This theorem is just part of a more general theorem called the work energy theorem. I'm going to make another video about potential energies and then kind of put it together. Right? So for now, kinetic energy is defined as energy due to motion. That's important. Right, this is how it's calculated. Kinetic energy is equal to 1/2 mv squared. Right, so it has units of kilogram meter squared per second squared. If you work this out, a kilogram meter squared per second squared is equal to a Newton meter, which is equal to what's called a joule. And this, I'll just say, first part of the work energy theorem says that, you know, a system will have a certain kinetic energy. If work is done on that system, add the work, the amount of work done, you now have the new kinetic energy of the system, right? And I'll be making more videos to talk about how potential energy and this go together and some examples. Have a great day.